Good afternoon, everyone. Thank you for coming out to join our session during lunchtime. My name is Caron Zhang, and currently I'm working as a senior machine learning engineer at Apple.
And I'm Ajay Vohra. I'm a principal generative AI applied engineer at AWS.
So yeah, today jointly we'll be talking about simplifying advanced AI model serving on Kubernetes using Helm charts. As we all know, AI is evolving faster than ever. But to reliably serve the diverse types of models ranging from LLMs to multimodal models to stable diffusion models and so many more on Kubernetes still remains a very challenging task. So in today's talk, we'll be sharing about some of the common challenges in bringing up this stack in Kubernetes faced by ML engineers like myself and the operations team. And then we'll propose a solution. We'll also show you a demo in the end to see how everything comes together. And we also will be sharing a QR code pointing to our GitHub repository for this project so that you can go home and try it out yourself. So hopefully at the end of the talk, you can walk away with some practical ideas and tips that you can apply to your daily work right away. So this is a quick look into our agenda today. We'll kick things off by providing an overview of the Kubernetes AI model serving stack. And this should be broadly applicable to all types of diverse models. And then we'll talk about the challenges in standing up such a stack in the realm of fast-evolving AI space. And then I'll hand it over to Ajay, who will talk about our solution and with two advanced examples. And in the end, we'll conclude with a recorded demo. So what does a typical stack look like in serving AI models on Kubernetes? Well, at a high level, at the most foundational layer, we have the hardware clusters consisting of machines, accelerators, network infrastructure pieces. And this layer is usually provisioned and managed by the infrastructure engineering team. And then on top of that sits the deployment orchestration workflows, which deploys the actual workloads to the Kubernetes cluster. And this layer is usually operated by the site reliability engineering team, or also known as SREs. And finally, at the top, we have inference servers, backends, the models of our choice, and various AI/ML frameworks to run the actual model inference. And this layer is usually implemented by machine learning engineers and used by application developers. So the focus of today's talk will be mainly on the first layer, and that is how we manage and deploy efficiently the diverse setups of AI/ML frameworks in Kubernetes without making any assumptions on how the setups are on the bottom two layers. But before we jump right into this top layer, maybe let's take a step back and just zoom into each of those high-level blocks to see what's the inner components that are building up to them. So we kept the color scheme roughly the same on this slide as the previous one, but at the first glance, it might look a little busy, so let's dissect it piece by piece. On the top left corner, where the red boxes are, this represents the service pod. This is responsible for running the actual inference service. And inside of the pod, we have the inference server, which handles the incoming request, outgoing response. And then we have the inference backend, which runs the actual inference engine or crunches the compute for inference to happen. And then we have the model itself. And supporting that are the various AI/ML frameworks, such as PyTorch, TensorFlow, and so on. And a runtime environment, if you're running on GPUs, it will be CUDA, and some collective communication primitives like all reduce, all gather. So that's the top left part. And if you shift focus on the right side, where the green boxes are, those are the Kubernetes constructs. The daemon sets integrate with the kubelet so that Kubernetes can schedule pods on the right hardware with the right storage. And finally, at the bottom, we have the device drivers, which connects the server pod to the actual hardware accelerators. Also the network drivers, which enables fast internode communications. And like mentioned, today we'll only be focusing on this top left corner where the inference stack happens. But in the GitHub link, which we'll provide in the end, it actually contains the full stack solution covering all aspects, including automatic node provisioning using Carpenter and cluster autoscaler. So let's dive right into this inference stack. And speaking of which, there is a broad spectrum of setups in terms of how the model inference is set up. So if we imagine the spectrum being like a horizontal line, let's say in the middle, we have the anchor point where one model runs comfortably on one GPU. Then on one end of the spectrum, we have the very small models which just need maybe a fraction of GPU to run. And then on the other end of the spectrum, we'll have the huge models which needs many GPUs to run on. So for this talk right now, we're not going to worry about this end of the spectrum where we need a fractional or one GPU per model type of setup. We'll just be starting at the point where we have one model which needs to be spread across multiple GPUs, exactly as depicted on this diagram here. So here, the model is spread across or sharded across 8 GPUs, but they're all fitting within the same node. But as the model sizes grow and as the context window length grow, we need more and more GPU memory, not just to load the model weights themselves, but also to have enough headroom so that we can have a sizable KV cache. Especially with the rising need of agentic AI applications, more often than not, we start to need to have this multi-node inference setup. So for example, in this diagram drawing, we have one model that's spread across 2 nodes and sitting on top of a total of 16 GPUs. For this diagram, just a side note, here under this setup, only the head pod in node 1 will be receiving the request and responding to the outside. But both the head pod and the worker pod will work together to run the actual inference compute or tensor operations. And we also call this setup having a tensor parallelism degree of 8 and pipeline parallelism degree of 2. So let's take a concrete example to perhaps illustrate things more clearly. Let's say someone wants to run a large open source model such as DeepSeek R1. We've been using the word inference server, backend models in the general terms, but for this specific example, let's say we want to choose Triton Inference Server as our inference service interface, which takes in requests and return responses. And then we can take vLLM, which is the inference backend, which runs the actual inference engines and compute on the hardware. And then when it comes to serving the DeepSeek R1 model, which by the way has 671 billion parameters, we could arguably fit all the model weights into one big node if that big node has, let's say, 8 B200 GPUs, under certain assumptions about the KV cache size. But oftentimes we need a large or larger KV cache size to get better performance, better throughput, and so on. So in that case, most likely, we'll need to cross the boundary of one node. In other words, having 2 of those big nodes of running B200 GPUs. Or in other scenarios, maybe we don't have access to the greatest and latest B200 GPUs. Maybe we only have access to H100 or H200 GPUs. In that case, we'll certainly need this multi-node inference setup. So the bottom line is, the larger the model size is, the more the longer the context length is of your prompt, then you more likely end up needing this multi-node inference setup. So now let's take this picture of the DeepSeek R1 serving stack and fit that into the bigger picture of Kubernetes serving in general. What else do we have? Well, in addition to the stack we just talked about, we can choose PyTorch as our AI ML running framework, which goes well with vLLM. And we can choose CUDA as our runtime environment. And we can use Nickel, which is NVIDIA's communication protocol, as our collective communications. So now this picture is fully painted. How do we bring each of these pieces into production? Well, first and foremost, probably some of you sitting here already are experiencing that yourself, is we need to figure out a compatibility matrix between the runtime and the device driver. And if you're running your workload on GPU, that would mean you have to find the right CUDA version, CUDA runtime version that works on your installed CUDA driver. And then we need to set up this hardware interface part. But fortunately, this part is usually encapsulated in the OS image itself. So as ML engineers like myself, we usually don't have to touch much. And then it comes to choosing the right AI frameworks, such as PyTorch, the right runtime, such as CUDA, and the inference server binaries of your choice, such as Triton Inference Server, and then the daemon sets. But fortunately, these circled boxes are also coming in with open source or vendor-provided container images. So again, we got lucky, and usually we don't have to change much. But serving a model is more than just having the right server binaries or picking the right Triton server. More importantly, we have to have the right set of configurations. Those configs are needed to, for example, launch the server with the right arguments, to define the model input, output formats, data types, to point to where the tokenizer files are, things like that. But this config, the challenge here is it varies across different choices of inference servers, backends, and the models, which essentially means this diversity in this inference stack leads directly to the diversity of the configurations. And aligning all of them to work seamlessly together becomes our core challenge. So to handle this challenge in config diversity, one option we thought of was, okay, we can put the configs in the image itself. But that slows down rapid development, because that essentially means for each combination of the server, the backend, the model, you would have to build a new Docker image for it. That is not really maintainable. The other option is let's externalize the configs onto a shared file system. But that breaks introduces challenges in reproducibility. Because when configurations are pulled out into the shared file system, they're decoupled from the Kubernetes deployment manifest, which means we no longer have a single unified record of the model, the code version, and the configs set to launch the server. So now we've established a dilemma. Embedding the configs in the image itself slows things down. Pulling them out into a shared file system breaks reproducibility. What to do now? Well, the solution is we need to use a declarative packaging tool to templatize the configurations, which should not only enable rapid iterations, but also ensures reproducibility. And to tell you more about that, I'll hand it over to Ajay.
Thanks, Caron. Okay, so our objective is that we need a declarative way to package everything and have version it, and then, of course, templatize it so we can manage it easily. And that's sort of like the North Star. That's what we are aiming towards. But before we get to that and kind of describe that solution in detail, let's touch upon something basic. I'm assuming a lot of you are very familiar with this, but just as a quick recap, how does an inference server stack actually run in Kubernetes? Well, essentially, you're going to have the appropriate resources within Kubernetes that map the stack. And the way you create resources in Kubernetes, as we all know, is you essentially express your desired state to the API server by saying, these are the API objects I want, and then some controller is going to be watching that and create the resources. So that's just a quick recap. But what kind of APIs are we talking about? In other words, what kind of API objects are we talking about when we're talking about inference stacks? So as it turns out, and this is, I guess, maybe slightly surprising, there's a very small number of Kubernetes APIs that really play a role in the entire world of inference in the context of Kubernetes. And one of the simplest APIs is, of course, deployment. And this is the API that you can use along with a horizontal pod scaler, a config map, and a service, and a persistent volume claim, which is the shared file system. So this collection, this set, can help you essentially work with single node inference very easily. And you can also horizontally scale it. So you can think of it as this is the baseline that would work in a lot of cases. Like, for example, if you were working with Triton Inference Server and you wanted to run any of the backends like TensorRT LLM, vLLM, Python, whatever, this would work, right? Okay, so we talked about that, of course, with increasing model sizes and context length, we need multi-node inference. So one option for doing multi-node inference in the context of Kubernetes is to use something like a LeaderWorkerSet, which actually conceptually works very similar to the previous case of using the deployment API, except you've substituted the LeaderWorkerSet instead of the deployment. And in this case, the LeaderWorkerSet gives you a hierarchy in terms of there being a distinct leader and then multiple one or more workers. And that allows you to create the topology for multi-node inference that you need, that the frameworks demand. For example, PyTorch requires you to have a master node and then the worker node, so it allows you to map that. And this would be perfect if, for example, you wanted to do, let's say, Triton Inference Server with the TensorRT LLM as the backend. So this would map very well to that. There's another very interesting API, which is the Ray Service API. And in some sense, this kind of combines the capabilities of the previous two APIs, because in this case, the service first creates a cluster, the Ray cluster, which is sort of like gives you the capability that the LWS was giving in the previous case. And then on top of that, the Ray serve maps the actual application. So you basically have a solution that gives you the distributed capability as well as the ability to run single node in the same solution. And we'll actually look at the multi-node inference example of this in a bit in the demo, as well as in the examples. But this sort of like unifies both the cases, single node inference as well as the multi-node inference using a single API, which is the Ray Service API. So now that we understand what kind of API objects we would need to do the inference stack in Kubernetes, now we have to basically figure out how do we do the packaging so that we can have versioning and we can have templatization. And so for that, we come to the core part of the solution, and that's basically Helm charts. So the idea behind Helm charts is that they provide you a mechanism called templates where you can define the API objects, all the API objects that you want to create in the topology that you want to create it. And at the same time, they have basically a Go templating engine available, and that allows you to do the templatization. So now you have all the pieces that you need. You have the ability to package the APIs that you wanted, as well as the configs and all that, and templatize it so that you don't have to have that problem that we ran into early on with the images where you're like constantly creating new images. In this case, the Helm chart itself will remain unchanged, and you can actually work with less than 5 Helm charts across all of the complexity of inference that exists today in the context of Kubernetes. And all you have to do is supply the right Helm values, and then you end up with the solution. So now let's look at some couple of examples. So the first example is the application of the Ray Service API that we just talked, but in this case, for multi-node inference. So as you can see, in this case, the requests are going only to the head pod, and then the model itself, again, through the pipelining aspect, is spread across the 2 nodes. So like tensor parallel degree 8, pipeline parallel degree 2. And of course, there's nothing magical about 8 and 2. Just keep that in mind, but that's just an example. You could have multiple nodes, you could have pipeline of 4, and spread the model across multiple nodes. So that's actually the example we will look at in the context of the demo. The next one is a bit interesting from the point of view of, to our knowledge, we have not seen this like out there in the literature or in the examples and so on. And this idea is that we basically using both the 2 cluster planes, the LeaderWorkerSet that we talked about first, and the Ray cluster at the same time. So they are sort of like coplanar, and the Ray cluster is being created on top of the LeaderWorkerSet. So in other words, you start off with a LeaderWorkerSet group where you have a leader pod, and then you have a bunch of 1 or more worker pods. And then from the leader pod, we use MPI run to fire off a cluster, like a Ray cluster. So now the Ray cluster is basically superimposed on top of the LeaderWorkerSet, right? And then whenever the LeaderWorkerSet scales, the Ray cluster is going to automatically scale with it, but the Ray cluster will always be contained within the LeaderWorkerSet. So you might be wondering, okay, but why? Like, what problem are you trying to solve by doing this? And the problem that we were trying to solve is we couldn't figure out how do you run something like a Triton Inference Server with vLLM. This might sound like, hey, that should be easy, straightforward, but we didn't find that to be the case. So I'm talking specifically in the context of multi-node inference. With the single node, it's easy, it's straightforward. But with the multi-node, running Triton Inference Server with TensorRT LLM backend was straightforward. That's like built in. But doing it with vLLM was not. So then essentially we basically arrived at the idea that, hey, if you have a Ray cluster already running on top of the LeaderWorkerSet, then what happens is whenever you use vLLM, vLLM is already integrated with Ray. So it's capable of automatically detecting that it's inside a Ray cluster, and it uses its distributed executor backend and basically makes use of that Ray cluster automatically. Like, you don't have to tell it, other than you have to say, I want this tensor parallel degree, I want this pipeline degree, and then it takes care of the rest. So you could have 4 nodes, you could have 8 nodes, which, by the way, you might need in a lot of cases if you have like A100 or H100 kind of machines and you have really large models, and it will basically take care of that. All right, so with that, let's actually, so we'll show this again, QR code for the GitHub at the end of the talk, but let's look at the demo. Okay. So this demo is it playing? Yeah, okay. So the demo is basically 2 A100 based nodes, like 8 GPUs in each. And we're running, let me actually pause that and set this up a little bit better. So what we're trying to do is, when you go to our GitHub, you will see a whole bunch of examples that already exist. Like think of it as like a little model hub, and you'll see a lot of examples with all the different types of things we discuss. But obviously, your first question is gonna be, I have a new model I wanna run. How should I do that? So this demo answers that question. And so in this example, let's say if you go to the GitHub, you will not see the model that is here in this example purposefully, so that you can actually, kind of try it out. And the model in this example is GPT OSS 120B. And so you say, okay, I want to run this model. How would I go about doing that? And so the demo explains how you go about doing that. So yeah, we're just starting over. So in this case, the key thing is we're using AI to help us generate the example. So we're using Claude in this case, and we're just going to say, hey, look at an example that already exists, and then just give me a new one, and here's what I want, like, tensor parallel, pipeline parallel, whatever. And it's basically using the, in this particular case, it's using Claude 4.5 Sonnet, and it's just generating the code for that example based on the pattern that's already there in your canonical example. And once it's able to generate the code, then we basically, there's like a Jupyter notebook you use to kind of walk through this process that we just described of like using Helm charts, applying the Helm values and all that. But all the Helm values that you need here are being automatically generated. And all you have to do is basically just run the notebook, and you get the answer. And you can do that pretty much with different types of models. So can you pause the thing for just a second? So we found this gratifying on two fronts. One was, if we are talking about a generalizable pattern, then it would be good to know that AI can quickly recognize it and basically spit out multiple examples without you having to do them again and again and so on. And all you have to sort of like tell is, in a declarative way, what is it you want, and it should basically figure out the rest. And we were pleased to see that it was able to do that. Pretty much the code ran without changes out of the box. And that was gratifying in that regard. The other thing I wanted to share is, as we were preparing this slide deck, we were using different AI models to kind of give them the slide and say, tell us, like, what do you see in it? And what we were surprised to see is that as we were going through the slides, it started predicting what it will see in the next slide. So we said, okay, this makes sense. We're probably onto something. And so we just wanted to share that tidbit. So go ahead and play. So I'll just let you watch the rest of it. So those are the Helm values in a YAML file. And that's all you have to, I would say that's all you have to write, but technically you don't have to write it. You just have to let somebody generate them. And then this is the notebook where you're just going to use those Helm values to do what you want. And you still have to do things like build a container if you need a container. So obviously you have to build the base container. Then you still have to download the model from Hugging Face, the weights, and put them on some shared file system. And then after that, you basically you just launch the service. And launching the service basically just means you take the Helm values that were generated, they're going to get applied to the chart, and the chart has the definition of all the Kubernetes API objects you need and so on. And the Helm values are going to get substituted into the templates, which are going to render, and you're going to get the manifests. The manifests are going to get deployed by Helm, and that means you have now a package, one unified package that has everything. You have versioning, it's templatized, it was automatically generated, and you can keep going generating as many more model examples that you want. And all you need is, and I say that all you need, but essentially all you need is the GPUs, which is the hardest part, we all know. But other than that, you can pretty much pick any model from the Hugging Face, pick your desired idea of what kind of things you want to do. And of course, you need this kind of experimentation because often you don't know the answer, exactly what you need, especially when you're dealing with new models for the first time. Okay. So that's it. Any questions? Happy to answer that. Yeah. Yes. I don't know if it's. Oh.
So just ask.
Yeah.
Yep, it's working now. Yeah, great talk. Why was Helm your choice and not writing a custom operator for this?
I think writing custom operators would solve a problem in a given specific thing. And then you are also creating a new API. Operators go with API. And what we were trying to do is not necessarily create new APIs. There's enough APIs that are out there. But we were trying to say, whatever is your favorite API, whatever is the stack you want to do, you basically should be able to do it. And there have been many attempts to write what I would call yet another API that's going to do it for everything. And we never found that to be the case. And those APIs have to basically evolve over a period of time to kind of just barely keep up with the rate of innovation of what's going on. And we thought this was maybe a more flexible approach.
Hi, this is Patrick from Anthropic. I have a question about the production scaling. What I see in the demo, you guys launched a particular LeaderWorkerSet and Ray service. So that is a single replica. So in production, you want to scale. How does that work?
So we didn't show this in the demo, but underneath the demo is like Carpenter. So that's the scaling mechanism. So at the top, you will just keep creating replicas of whatever the API objects are, like LWS or just Ray service. And then whenever there's a scaling of the pods, it will automatically scale the scaling of the nodes at the lower level by Carpenter or cluster autoscaler, whichever you want. So that's the scaling mechanism at the infrastructure level.
Okay, so does it work by creating more and more LeaderWorkerSet?
Exactly. So that you'll create more, and of course you can start a desired state at the beginning, which could be more than one, obviously, and then the max. So you can set the collars, the bookends, but within those bookends, it will scale automatically up and down.
Cool. Thanks.
Yep.
Super interesting. I'm curious about the templating. I mean, that could be considered a spec in spec-driven development. Do you think of it that way? Like Claude Code is spec-driven?
Yeah.
Right?
We thought about it that way, but the problem is, as soon as you do that, like as soon as you define a spec, then it can only handle so many things. And what we said was keep it just completely open, and whatever the chart you define, that chart is what you want to instantiate, and then whatever the values that chart needs is your values file. And so we just keep it completely open-ended. But having said that, when you actually look at the examples, you will see immediately there's a pattern, and most of the things are like in the same, but we didn't go to the next step of defining a spec or anything like that.
Okay, the second part of the question is, if you had done that, could you use K-agents to automate all of these experiments?
Yes, theoretically, we haven't tried it, so
Okay.
There may be a difference between theoretical concept and actually working it out, but yes, because in some sense, when the demo, if you saw, was already an agent doing all the work. The whole creation of everything was being done by the agent instead the IDE, that the example I was using, Caron. But you can think of it as that agent was using Claude, the LLM, to create the whole thing, and then running the notebook was essentially the only bit. Okay.
Thanks.
Yeah. So okay, last question.
I actually just have a comment on the scale. I think the question was more about like scalability of the solution, not how you auto scale.
Yeah.
I just want to make a comment on LWS. It builds on top of stateful set, so it inherits all the scalability, characteristics of that.
Yeah.
So that's a design decision from AWS. Doesn't try to reinvent the wheel.
Yes.
Builds on top of like bulletproof or like battle-tested APIs.
Yes, and I recognize you from some video. Are you involved with LWS?
Yeah.
Oh, I think so, yes. Okay. Thank you so much.